I need to copy the papers. Keep it. Give me. Yeah. So I have kept both the files. PPT and PDF. Both can be copied. You open the book of names. So 120 up 1, the first top one, which is corresponding of one source file. Here, इसके पीछे से ओपनिंग होता है इधर नो तो अगर अगर ओपनिंग होता है तो आवाज पड़ गई and I was told इसको टर्न करके ऐसे thank you so like is it like my will be one after another or like how ठीक ও তাই হ্যাঁ 10টা 5 হ্যাঁ তাই তো করতে বললাম
on Good morning, everyone. Welcome to the third day of Day 23. We'll start our day with a technical session on signal processing. And to chair the session, I would like to request Professor Shagupur Dash of Indian Statistical Institute, Kolkata, to please come on stage and chair the session.
The mic is available. Very good morning to one and all.
Good morning, everyone. Welcome to this particular session on signal processing at the Day 23 conference. May we call for presentation of the first paper with ID 020. Its title is Heterogeneous Stacked Ensemble Framework for Surface Electromyography Signal Classification. You will present, okay, please. You have 20 minutes, including question and answer.
Very good morning, all of you present here. I am Somen Gorai from NIT Durgapur, PhD scholar. Today, I'm going to present the heterogeneous stack assemble framework for surface electromyography signal classification, that is ACMG signal classification. So these are the content today we are going to cover. That is ACMG signal classification and its application, end-to-end pipeline of the system. Major highlight about our work, a description of data sets, feature extraction process, supervised learning, stack ensemble framework, which is classification framework, experimental setup, result, and conclusion. So ACMG signal is a technique which detect the electrical signal under the surface. So under the surface, it involves number of electrodes on the surface of the skin, which detect the electrical signal and amplify the signal when the muscle contacts. And this signal is essential for the accurately controlling the device like posterior devices. Not only for posterior devices, we can accurately control the wireless controlling device like the gaming control device. So this is the end-to-end pipelines process of this our system. So it is starting from the raw data capturing from the upper limb of the human, and it is after some preprocessing unit feed to the feature extraction set to extract the underlying feature of this raw signal or image signal. Then it is passed to the pattern recognition for the classification of our classes. So this is the figure of capturing the data from the upper limb positions. So during the data collection, we have to take in mind some important features, important points like a number of electrode. So here in this figure, we are use 7 electrode. It's maybe more than 7 electrode or less than 7 electrode, but 7 electrode because it covered the surface area. Whatever, if you use more electrode, it will cover more surface area and get more features from this. If you less surface area, cover less surface area, you will generate less signal from this. Force applied, that is the electrode which are applied on the surface of the skin. The force applied on the skin, it also affects the data collection. And the most important is the limb position. Though the limb hand movement, hand position is also very important, which are going to discuss in the further slide. So the major highlight of our work is that we in this study we explored the heterogeneous stack heterogeneous assemble framework for classify the multi-class classification of the upper limb position using the SENG signal. For the data set, we use 7 electrode and 5 different limb positions. And for the feature extraction, we use correlated time description features extraction process. And the classification we are use heterogeneous stack assemble framework. Previously, there are some work on the SVM classifier or the MLP classifier, but these are not accurately properly work on the real-time scenario. So, today's area is the deep learning network, but like this type of experiment in a short data set is there, so it is not possible to feed this model to the deep learning network. And on the other hand, the random forest using the heterogeneous classifier is very populated like this way. So this for this reason we use the stack assemble framework of our work. So this is the data description. So data is captured upper limb position of the human. It is a non-invasive method, that is no electrode is injected inside the muscles. Only the electrode are placed on the surface on the skin, so that no surgical process is done, and it gives the less infection. Here we use 11 subject and seven electrode for collecting the data. These are the limb positions, whatever we said, that is P1, P2, P5, different limb position is there. And for the classification, we use 8 classes, the C0 to C7. These 8 classes are used for the classification. So why we considering the limb position? By considering the limb position during the time of the training, we can accept a better accuracy when we perform in the real-time scenario. The human can perform any gesture, any hand positions. So this type of data set is very useful for the controlling device like positive device robotics arm. For this reason, it is very useful data set. Now come to the feature extraction. So feature extraction, basically here we extract the power spectral density feature from the EMG signal. First we make a window of 100 millisecond and a sliding window of 25 millisecond for the better continuity. From this window we extract 6 power spectrum features. These are the M0, M1 as mentioned here. And these features are called the time domain description feature. Combining these time domain description feature, we generate the correlated time domain description feature, and these are useful for our work. Here, basically, dimension of this feature is 42 because there are six CTD feature is extracted, and the 7 channel is there. 7 electrode are there, so 7 into 42, 7 into 6 is 42 dimension feature is extracted from this work. So as it is supervised learning, this is the general structure of the supervised learning. So supervised learning is deal with a labeled data set which like x1, y1, x2, y2 up to x10, yn. So here the x belongs to n cross d. D is the dimension of the features. Y belongs to n cross 1. But in this case, it is a multi-class scenario. So it is y belongs to n cross c. That is c is number of classes. The main objective of this supervised learning is that using the design matrix and the label data set, we have to learn the hypothesis and the function of x so that we can the h of x can predict the output y. Now come to our classifier, that is the stack assemble classifier. The stack assemble classifier is a machine learning technique which combines the prediction of the base classifier using the meta classifier on the top of this. So these are the base classifier, and these are the meta classifier or the blinding. So here the base classifier is performed individually and predict something. From this prediction, the base meta classifier learn and give a better accuracy for our model. So this is the training process of the stacking ensemble training is done. So to start this training, first we divide this our training set into two data sets, subset 1, subset 2. Using this subset 1, we train the base classifier first individually, and using the subset 2, we predict this base classifier. First train, then we predict the base classifier, get the prediction on the subset 2, and using this prediction we train the meta classifier. So this is the training process of the stack ensemble framework. So this is the architecture used by our work. Here we use heterogeneous stack ensemble framework. Why it is heterogeneous? To get the maximize our stacking ensemble advantage and reduce the biases of the base classifier. So the base classifier are here. The KNN are LR, DT, and SVM is the base classifier. We train it after this prediction. We get a new data set on the base of the prediction, and these predictions are fed to the meta classifier. Here we use two meta classifier, that is the RA and the MLP. So we train this meta classifier using this prediction data set, that is new data set, and after finally we can test our model. So experimental setup. This experimental is performed on the Python 3.8 versions, and the Python libraries like machine learning extensor library used for the stacking ensemble API. Grid search used for our work for the hyperparameter tuning, and obviously this is a subject specific multi-class classification. That means if you change the subject, we have to again start from this. We have to again start from the zero, because if you change the subject, that time we have to train again, and you have to run the prediction. This is the data set. This is the data set distribution. So for the training, we use the position, that is P1, P3, and P5. And the test set, we use two set tested here. There is one test set is for the P2, P4, and another test set is for all the positions. So this is the experimental result. Here all the classifier, base classifier, and these are the meta classifier is here. The parameter, what are hyperparameter tune here, these are written here, and these are the accuracy, and the F1 score is shown in here. So from this experimental table, you can easily identify that the meta classifier is perform better than the base classifier, and for the dataset 2, and also the meta classifier, between these two meta classifier, the random forest meta classifier is performed well for the dataset 2 also, because the dataset 2 contain all the positions in this dataset points. So this is the GitHub link of this experiment. Now to come to the conclusion. So our main objective is to reduce the generalization error. So it is done by the stacking ensemble learning. It shows that the accuracy improvement is done approximately 5.6% on the meta classifier. For the future work, the same process can be done by the deep learning network in near future, and the complexity of the system can be reduced by the raw image signal as a word, rather than the feature extraction step. Thank you. Any questions?
So any question from the audience, please? Here's a question. Yeah? No question. Okay, so I have a couple of things to understand. First of all, you are using stacking ensemble with two meta classifiers. That's fine. But did you compare against boosting kind of thing, error boost or gradient boosting?
Sir,
Which would be
Actually, our previous work is based on the boost stacking and boosting this one. So in this work, we are using the ensemble framework.
no, but in this work, you are not comparing against those methods like error boost or with stacking, let's say.
No, sir, we are not, right now, we are not compared, but in future work, it may be included on this.
So what prompted you to take MLP as a meta classifier?
Because the previous work in our literature survey found that MLP and SVM perform well for the classification. This type of
That's
classification.
right, but when you are building the ensemble, usually people take weak learners. Right? SVM, you are using SVM as a base classifier in your ensemble, right? And SVM is a strong classifier. Usually it's very hard to change the decision boundary
Yes.
unless the support vectors themselves get shifted. So that's somewhat counterintuitive and might be some more reasoning would be essential for that particular component. Okay, so let us thank the author for this presentation. Thank you very much. And let's move on to the next one. I think the next paper is with ID spatiotemporal co-occurrence index using spatiotemporal variability signals. And may I call Rahul Dasharath Ravas for the presentation, please?
Hello everyone. My name is Rahul Dasharath. I'm from Bangalore, and today I'll be presenting a work titled Spatiotemporal Co-occurrence Index using spatiotemporal variability signals, done under the guidance of Dr. Soumya Ghosh and Dr. Kumar from IIT, and also our co-author Day3 strategy from PCSS. So, firstly, in our work, we are trying to model the co-occurrence patterns in spatiotemporal signals and come out as an index, which will define how much co-occurrence is there between climatic signals taken from different zones. So coming to the co-occurrence, so it's like given a feature, how they frequently occur with respect to each other, that is co-occurrence. And for different target data sets, we have different kinds of co-occurrences. So in case of transaction data sets, we have rules of association. And in spatial data sets, we have spatial co-occurrences. And spatiotemporal data sets, we are coming up with a metric here in this work. And this can find applications in economic planning or noise removal or sampling of different zones when it comes to climatic data. So in this work, we mainly targeted Earth's mean temperature as our target signal from different geographic zones. And it's like tracing the thermal tapestry across zones. So it's like a blanket of thermal signals across zones and how they co-occur with respect to each other. That's our target. So with that aim, we try to come up with a metric which will be a metric across signals taken from 2 or more zones. And we are mainly interested in the frequency components in the climatic signals. And if there is variation in one zone, then it should decrease the overall score. So in that regard, we came up with this signal, which we call spatiotemporal variation signal. So the x-axis is time, y-axis is amplitude. So at any one time instant, if you take the any 4 or more than that zones, and the green color indicates the amplitude of the radius of the circle indicates the amplitude of the temperature signal. So it's like if all the 4 shown here circles are having same radius, then the variation is less and it's almost around 0. But if 1 or 2 of them change in amplitude, then they pull it up. So the variation is high. So like this, these zones pull or push the variation, and that gives rise to this red color signal called the spatiotemporal variation signal. So this signal embeds the nature of co-occurrences between the n number of zones considered. So let's have a look at how the signal behaves. So to start with, we started with collecting data from 4 small cities of Karnataka, Karwar, Ankara, Bhopal, and Punjab. So this is temperature signal from 20 years. And then the bottommost part is the spatiotemporal variation signal. So the first towards the figure B, if you see, it's the frequency spectrum from Karwar. So we see here the annual component, semi-annual component. The third component is missing here, and that is a quarterly component. However, when we see the figure C there, which is a spectrogram, frequency spectrum of the spatial temporal variation signal, we see the missing component coming here. Now that is because city Karwar is slightly urbanized compared to the other three, and that is adding to the variation. So such kind of variations can be detected using this signal. So to come up with a score, we first looked into the features. So there are pulse harmonics here as we saw in the previous slides. So we took the power corresponding to this pulse harmonics, and then we took data from 20 clusters of near zones and 20 clusters of faraway zones. And when we do a box plot of the features, we see that the annual component is very well distinguishing, and the third and the fourth component also, whereas there was no much distinguishing factor in terms of second component. Then we use this scoring mechanism to quantify our findings. So we take the midpoint of the distributions, and that defines our omega m. And then we use a sigmoidal function to come up with a score in the range of 0 to 1. And that is the equation. And the objective here is to have the score maximum or almost 1 when all the signals from Z number of zones are same. And delta is a scaling parameter which defines the range of the sigmoidal function. So to select the optimal delta, we started with 0 to 100, and then we found the distance between the separation of the metric for near versus far zones. And in the second derivative, we find an inflection point, and that gives our delta value for us. And when we have multiple features to consider to come up with the score, we use a weighted average to get one single score out of multiple features. Then we initially started with some simulation to see how this SVS signal looks like. So in case one, we had signals, all the signals from Z number of zones to be same, just like they are collected from very close by regions. In case two, we had signals varying in amplitude. Then in case three, they varied in phase, and in case four, both amplitude and phase. So it looks something like this. So case one, all the signals are same across four zones. Case two, they are increasing in amplitude. Case three, there is change in phase. Case four, phase and amplitude both are changing. So when we consider the SVS signal and compute the power, so we see that in case 4, all are 0, which is expected because there is like all are same and it is like a DC signal almost. In case 2, the pattern corresponding to the raw signal is maintained. That is, the power of frequency 1 is greater than the rest of them, and it forms a staircase like a thing. But in case 3, where the phase was changing, so we saw it distorts the complete pattern of SVS. And in case of when phase and amplitude both change, amplitude becomes more dominant. Because of that, we still see the same nature. So on real world signals, we tried this. So we had 20 clusters of near zones, wherein each cluster consisted of cities taken from a very close by radius, maybe from the same district or same state. In far off zones, we had 1 or 2 cities coming from different continents or Earth. And when we see our score, we can see there is a good separation there. And to compare with the raw power value of the annual component, omega 1, so there is separation. However, that separation further improves when we quantify it like this. So let us have a look at 4 extreme cases. So in case 1, yeah, we have among the 20 cases for near and far, we can just show 4 extreme cases. So in case 1, we have 4 small towns from Karnataka, and these are from western parts of Karnataka. So all of them have similar climatic conditions, heavy rainfall, and totally covered with thick forest. So as expected, the score value is high here, and the maximum distance between any one city from the rest is around 80 kilometers. And but when we consider 4 cities from Punjab, Faridkot, Firozpur, Jagrao, and Moga, we see that the score value has decreased a bit. On further exploration, we found that Jagrao and Moga have different climatic conditions, are very humid compared to Faridkot and Firozpur. Then, considering the far off case, we took data from these 4 cities, which are very far away from each other, and as expected, the score value is very less. However, when we take data from these 4 faraway cities, we see that the score value is almost around 50%, around 0.47. Now, the reason being here is this 2 cities, Dhaka and Solapur, they are near to the equator and have similar climatic conditions because they lie on the same isothermal belt, whereas the 2 cities at the top are on the same isothermal belt and are very cold in nature. So this 50-50 kind of thing is bringing the score down, bringing it towards 0.5. So to conclude with, this work targeted to come up with a score to model the spatial temporal co-occurrences, and we mainly targeted the frequency components in it. And in future, we would like to try this on different climatic variables like precipitation, humidity, and also try to fuse them to see if we can detect anomalies or any climate change. Thank you.
So let us thank the speaker for the presentation. And
If the audience has some question, please go ahead. Yeah.
Thank you very much for your presentation. I have a question. What is the actual application of this particular work? So I didn't get it.
Yeah, so application we have split here in this paper because of lack of space. So mainly when we are building a model to predict some climatic condition or classification model basically, and when we sample zones, geographic zones, so we tend to think that if we are taking close by zones, then they may be similar in nature and we can build a model to that particular region. But even though they are close by to each other, due to some urbanization effects or some anomalies, they may add more variance to the overall model. So this kind of score can help us to select which zones will have the data with more co-occurrence. In that way, we can use it, and also we can use it for noise treatment.
So your work actually it depends on demographic condition, different demographic condition. So suppose in a particular region, the weather changes very frequently, but the distance is not too far. Then your work, this particular work, can be applied in that situation? Or
Yes, we can apply that. If you are taking temperature signal there, and because of that weather condition, is temperature signal is getting hampered, then the score value will be less.
You said you are simulating some signals, right? This is various kind of signals. How exactly you are simulating them? Just elaborate a bit.
Yeah. So we simulated by considering the real world signal. So in the real world temperature signal, we see that there are four dominant pulse harmonics, and they follow this relation that the first one is greater than the second, then third, and fourth. So
So you just maintain that constant and generate around the same similar frequency scale.
yes, yes.
But usually in climatic informatics or this sort of situations, a lot of noise are there. There is a noise envelope on the signals.
Yes.
Did you consider that?
Sir, currently when we saw the noise spectrum, sir, the noise component was like a white noise, and it was slightly lesser.
It's a full white noise.
Yes. Yes.
So you already suppressed that, and you assume that it is suppressed. And
We
then
assume
you
that
are-
it is suppressed. Yes. So
Okay. Okay, so if there is no more question,
thank you very much for the presentation.
let us move on to the next paper, which has the title Noise Robust Whispered Features for Diacertic Severity Level Classification. And may I call upon Hemant A. Patil for the presentation, please.
Yeah. So I'll be presenting a co-author research paper, Noise Robust Whisper Features for Diacertic Severity Level Classification. On behalf of the co-authors Siddharth Rathod and Munil Charola. In fact, they were the final year students when this work was done and the paper was submitted to this final year BTech students. So dysarthria, of course, it is neurological disorder. So that causes difficulties in producing natural speech. Coordination between the brain and speech producing muscles is disturbed. Often classified into severity level classes based on intelligibility of speaker speech. So that is the problem, the topic that we are going to address. So applications of this problem, that is applications of dysarthric severity level. So professional can design a personalized course of treatment based on severity level of the dysarthria of the patients. Assistive technologies such as automatic speech recognition for the dysarthric speech could benefit from severity level classification. In particular, if we know the severity level of a particular, dysarthric speech, then we can invoke a particular speech recognition model to improve the performance. Further, in remote areas where clinical facilities are not available, so remote or online classification system of this kind would be very useful. So proposed work, of course, here we are using whisper-based deep learning model. So it is using the pre-trained whisper model proposed by OpenAI very recently in September 2022 to classify audio samples into the severity levels. So this model means whisper actually means weight scaled supervised pre-training for speech recognition, and it is based on transformer model, which is trained on very large amount of data of the order of 680,000 hours of labeled audio data scrapped from the internet. We propose whisper encoder based features and output as features for severity level classification, and the classifier uses CNN. Well, what is a whisper model? So it is basically trained on a large web scrap audio transcription data set. It is an open source ASR model developed by OpenAI and released in September 2022. Whisper is derived from the acronym WSPSER, which stands for Web Scale Supervised Pre-training for Speech Recognition. And the main motivation behind the Whisper is that training on substantial and varied data set improves the performance of the system. So, historically, Whisper is proposed for the speech recognition application. Here, we are using that model for the dysarthric severity level classification. Here is an architecture of the model. So, of course, as for many deep learning algorithms, you can see that from the raw audio waveform, first we represent this into the log noise spectrogram. This is indeed the case basically for many ASR applications utilizing the deep learning approaches for the speech technologies. Then it is passed through the convolutional layers. Then it is having the sinusoidal positional encoding, and then there are several layers of encoder block. From then output of the last layer in this particular paper, we extract the whisper features from the output of the last layer, and then that is being given as input to CNN classifier. So here there are depending upon the types of model of the whisper, it can be starting from as low computational complexity as like tiny to the large model. The number of layers, the number of hyperparameter, all will increase almost exponentially. So in this work, we use the two basically models, that is the base and the tiny model. For the problem, we use basically standard data set to train, so the data set used for, the system, the data set created to train the whisper model consisting of 680,000 hours of label data. Out of this, 117,000 hours of data is for other languages, then 125,000 hours of data is translational data, that is audio is of another language while the transcription is in English. This results in a diversified data set encompassing a wide range of sounds from different and acoustic environments, recording setups, speaker and language. So as I said, we extracted basically the features from the last layer and gave it basically input to the CNN classifier. Then the data set used for this work is basically Talgo corpus. It is also one of the standard corpus along with the other corpus used in this area, that is universal access UA corpus. the baseline system adapted for the download data set had 1982 training files and 199 testing files. So there are three dysarthric severity level in this corpus. One is very low dysarthric level. This is the file ID. Low dysarthric level, severity level. This is the file ID, and the medium severity level. So results. So of course, one of the things that we did here is to investigate the robustness of the proposed feature. So to analyze the noise robustness, we use two types of noise, that is additive white Gaussian noise and babble noise. Babble noise is very relevant for this problem because if the recording is done, of course, many a time in the hospitals, so there is always a crosstalk from the other, members, people present in the hospital. So babble noise is very relevant for this problem in the medical domain. To further analyze the impact of noise, we have used basically SNR level impact, from let us say 10 dB, we go to 5 dB, 0 dB, and also till -5. So you can see here we have used two models. One is timing model, another is a base model. This represents actually the number of hidden layers and the hyperparameters used. So there is some performance improvement for the base model, given it has a more number of layers than this one. So therefore, if we go further for the large model and all, but it requires, of course, a huge amount of computational power and resources, we expect to get better results further. Then with this again, the base model, what we did, we compare the results with the standard baseline feature set like MFCC, and the proposed feature set basically this bar represents the whisper features. So you can see that, of course, both the systems are developed using CNN as a classifier. So when we go from, let us say, clean to noisy degradation, naturally the slope of this trend line decreases, indicating that in the presence of noise, the performance of the severity classification system degrades. That is very sure. Plus, you can see here the slope of this line is lesser compared to the slope of this line, indicating this line is for the baseline features. So you can see the degradation, the relative degradation is very severe for the baseline system, but however, the relative degradation for the proposed feature set is less severe, indicating that even in the presence of -5 decibel as a signal degradation condition, still the performance is not degraded, as it is the case for the MFCC. You can see that there is almost 15% or 14% of performance difference here. So this is the one of the noisy robustness analysis. Then we also experimented, the same thing on same noise robust analysis for another kind of noise, that is AWGN noise, and there we found basically babble noise. So you can again see that the performance of the proposed feature set is a lot more better for each SNR level, and of course the degradation here still basically of the order of 5% for every SNR level. So you can see that the whisper model performs better than the existing features by a margin of 5% accuracy. In addition to the noise robustness, so one of the things that we should see that why the proposed whisper model is noise robust, because as I said, it is trained on very large amount of speech data from variety of acoustic environments, recording conditions, speakers, languages, transcription. So the model captures all possible variability in the speech as of now. That's what the claim, and also which is why it is trained, because it is trained on very large amount of data, so the noise robustness is captured in those parameters. That is because it's a pre-trained model and we are using the features at the encoding. Further, to see the practical suitability of this proposed feature set, we experimental as the latency period, meaning for how much minimum amount of speech segment, this is in a millisecond. So you can see that for 100 milliseconds, the baseline system gives 64% accuracy, whereas at the same speech segment, the proposed feature set gives 93.47% accuracy. This is indicating that for the least amount of feature set, the speech duration, this gives a reasonable accuracy, and it settles down more or less at 200 milliseconds. You can see that the slope is almost zero here, but here there is a significant performance degradation if you decrease the amount of texting speech, indicating that the proposed whisper-based approach may have, significance for the practical deployment of the such kind of civility classification system. So to summarize, in this work, pre-trained speech models, a large and diverse data set improves the performance for dissertative level classification. Overall, this study highlights the potential of utilizing the pre-trained models for developing novel features for speech-related problems. The large and diverse data set used to train whisper model allows to capture a wide range of speech characteristics and variations, acoustic variations, making it more adaptable to different environments and microphone setup. Thus, in turn, leads to better performance for the whisper encoder features in my application, such as dissertative civility level application. So there are some open problems in this area that one can even experiment on which encoder layer is giving the better performance than only the feature extracted from the last encoder layer. And we can even tune the hyperparameters which is produce civility level classification. So this is also the work that has to be done in the future. So thank you.
Any question from the audience, please? Any question? I have a couple of points for you. First of all, you are using this transformer encoder, and therefrom you are extracting the feature, feeding it into a standard CNN workflow to do this. So, who is specifying the severity levels of the dysphotic disorder? Your classification is aimed at detection of the severity levels, some kind of staging of the dysphotic disorder, right? So the class levels are fixed by the data set itself.
Yes. So here we have taken this data, and these are the class levels. So these numbers indicate that.
Yeah, exactly. That is the question. These thresholds, let's say, very low, medium, these are fuzzy kind of sets, or these are very crisp kind of classification?
So the real answer to this is fuzzy kind of because this is labeled by the speech intelligibility test. So it is done by the human listener. So it is definitely
subjective and fuzzy.
Cognitive, so fuzzy.
But when you you are using a hard boundary between different classes. Right?
This is the issue in many such kind of works where, for example, even in speech coding or speech quality evaluation, we ask speech synthesis, the quality of synthesis speech also. The issue is that when we do the mean opinion score, then we are asking the listeners to listen and rate the speech quality based on 0 to 5 score. So that is subjective, and the challenge is to develop an objective measure, which is very, very difficult problem. In fact, the first research paper appeared in the history of speech literature on evaluating this, linking the objective measure versus the subjective measures of speech quality, not for dysarthria, but for the speech synthesis, was in 2012. So the problem is terribly difficult. The reason is the rating given by the human subjects are highly subjective because every person will have different cognitive factors, different environment in terms of when they are listening, with respect to from the environment they come from, and the mental state, emotional state, many factors.
And obviously, I mean, the next stage.
So therefore, this is a discrepancy. The label given by this one is used as a hard label as for us by us.
That is one, and then obviously one of the major next step should be the dysphotic speech correction. And generative AI models, as far as I can see, they could be like this voice GAN or similar things to synthesize correct speech segments from these disordered speech segments. Can your method serve as a beginning tool for that?
So see, here this particular problem, what it does, it tries to find the efficiency of a classification system to label unknown sample and at what level the dysarthric speech is there. So, as of now, one thing is very sure in the literature that this labeling will help to route the speech utterance of a particular dysarthric severity level to a particular model. Maybe I see almost less work or no work in the direction that you indicated, and it's very interesting. Like, what, for example, you're talking about the GAN. So in the GAN, this simulated level can help. So in the GAN, let us say it's a primitive GAN. I'm talking about the basic GAN. Vanilla GAN, where there is a basically discriminator and where there is basically the generator. So this simulated level classification may help that for the discriminator, what is the ground truth? Let us say, if that ground truth is now traded off with the at epochs interval, how much the generator has to struggle to produce the output. So, if we know the severity of the ground truth given to the discriminator, we will be able to trade off the number of epochs required for the generator to converge and to fool the discriminator. Is my understanding.
Right, that's the nice take on it.
So, and thank you very much. In fact, this I never thought. So I am very happy that by presenting this paper, I got this idea. Thank you.
Thank you so much for this presentation. Okay. Now let us move on to the next presentation, which is Multilingual Speech Identification Framework, MSIF, a novel approach in language identification to be presented by Swapnil Sarankar. Is he here, the presenter? Okay, sure.
Good morning, everyone. Respected chair and my colleague. Myself, Swapnil Savalkar, and I'm going to present my paper on multilingual speech identification framework. That is a completely novel approach on a language identification. My co-author is Dr. Pinky Roy, who is the associate professor and head at NIT Silchar, and I'm working with Signa College of Engineering and Technology, Amravati, and part-time PhD scholar of NIT Silchar. Here are two contents that platform abstract, introduction, some of the literature survey, the experimental setups, as well as some performance measures I'm just going to cover over here. Then identified with some research gaps, as well as what are the data sets I'm just going to explore in this research area, and lastly the conclusion. As far as this language identification area, this is a very widely popular area which has various applications, just like ASR, IVR, or even the Google Assistant. Somewhat where this LID is used for automatic call routing, customer calling, or can just say call centers, that is benefited. So this area is highly demanding and have a lot many models to be implemented along with some the deep learning methodologies or machine learning techniques, along with most of the various techniques used. There are a lot many models currently existing or particularly working on this area, but there are some loopholes, some limitations. And my proposed framework that I am just going to propose here is somewhat kindly having some improvement over these existing models. While introducing my this novel approach, that is multilingual speech identification framework, that is this supersede model over the existing models, which have certain specific language oriented or bias oriented certain features, just like accents, dialects of language. In case of most of the regional language, basically I'm doing this research on Devanagari languages, that is Indian regional languages. These basically are the focus of my research area. This proposed model basically proposes with the hybrid approach, that is, it's used with the CNN and bidirectional LSTM, along with the attention mechanism. That is three kind of the techniques we are just focusing over here. just to improve the performance measures in case of language identification. Now, this is the diagram which is having some basic building blocks. That is the speech samples going to convert in the spectrogram images. Then it is there is a part of the pre-processing, and then it is given to the GAN and CNN, but along with the bi-LSTM, that is I'm forget to mention earlier, and that is basically the phase of the uh, categorize the training sample as well as testing sample, which is then given up to the particularly process of validation and optimization of all these samples. And lastly, with the score matching, we are just used to identify the language, the particular language in this. So I'm just going to introduce in brief that is about this proposed model, and just using the first of all the GAN that is generative adversarial network along with the bi-LSTM and CNN. These are the three combined mechanism we are just using just to specifically processing high audio waveform, generate audio. Then CNN just to extract some of the features from the data inputs. There is one process that is known as a transfer learning, which is basically a very important or crucial part of this area. That is, it is just used to possess some kind of knowledge, some kind of information which is from the past as well as currently it is processed with the current observations. So combining that, it will improve with the dialect variations in the language which is to be identified. And bi-LSTM, that is the common well-known technique normally used for basically the highly accurate language identification with the correlating the some of the features from the basic audio. So here is the diagram. This diagram having the three components, that is generative adversarial network, that is CNN, as well as lastly the dual attenuative memory network. Now, middle one is a super enhanced neural network, that is the combination of CNN and bi-LSTM, and generative adversarial network is normally used for generating most of the samples. It is just like working like generating more and more samples along with the discriminating most of the samples for identifying the accurate samples. They are just like a min-max type of logic, which is particularly one component is normally used to increase the number of data points in the particularly collection, and another is trying to reduce the output. So in this basic mechanism, lastly the accurate points are going to be identified and covered with this GAN. Next is the CNN, that is basically using the bi-LSTM to the classify or feature extracted some of the features from this. Last is the dual attenuative memory. This is used basically the memory network, which is the neural network part, and that is going to train with the or portion with the training as well as testing of the data, and then train with some of the samples, and lastly going to basically under the validation of the testing, it will be come out with the most accurate result. Most of the advanced features of the speech identification. Now this is another the process flow of a device superintendent neural network. So here I'm just focusing on those four basic regional languages of Devanagari, that is Gujarati, Marathi, Konkani, and Hindi. These are the speech corpus. Speech corpora, they are just used with the GAN network, and whatever the output, these are particularly fit to a CNN and bi-LSTM just for the separation as well as the dropout of some inaccurate samples, and then come with the feature extraction lastly to identify the audio or language identification. This is some of the literature surveys I'm just particularly observed from the some of the papers. Like first paper is Himanish Das and Roy Ma'am. These are particularly work for the same model, that is CNN and BILSTM model, but having some limitation that it is basically using the real-time data that some of the speech corpus are already recorded in the lab of the NIT, and they are working on that. So this is having some kind of having some kind of limitation as well as there is work for some kind of data sets in good manner. So it gives the accuracy 98%. Likewise, there is a certain another important survey on basic papers, just like methods LXNet used by the Rao and Agla. Then the model will be come up with the accuracy of 83.5. Likewise, some BGG 16 as well as some V3 ANN model having used with the data set that is IITH Fox Force and having a 97% of the accuracy. These have some kind of the limitations as well, that they are not used with some complexity kind of the data sets, which affects complexity time as well in the output. Then rest of the model with the survey, which gives likely the LAHC or BBF based feature selection model giving accuracy up to 92.3, as well as some fuzzies GCP model, DCN model with the accuracy 81.5. So these are the some papers. I have taken this as a survey. The proposed solution, that is, it is one of the promising approach that that I observed that used to identify the languages, spoken languages of speech data, which normally work on the superindexed neural network with the data augmentation and feature extraction. Dual alternative memory network is generalized mechanism for language identification. This is the hybrid approach, which will enhance basically the accuracy and identification process, and which improves the model robustness at class. The proposed framework, it is basically counted in terms of accuracy, resilience, and some of the most important features of a language identification. So basically, I am using in this hybrid model with the GAN and CNN along with the YLSTM, but basically work with the LDC and IL, the Language Data Consortium, and Indian, for Indian language, that is particularly the data set available with the most of the speech corpora with 4 languages. That is, I'm working with the. Then this particular model used to work with the feature extraction from audio in basically the transfer learning for capturing or preserving some patterns, that's audio pattern, using this ILSK. So this is the basic formula for this, basically the GAN, working of GAN, that I think everybody knows. So it is having some discriminator as well as the generator. These are the 2 major components. These are used to particularly work with the GAN for exactly identifying accurately come out basic points results from the this model.
Yeah, I think you can skip the basic details.
This is a experimental setup that I just worked on this ideal LDC ideal data set with the limited data sets, and I'm currently working on the higher side complexity data set. So these are the particularly the results. Then performance measures, that 3 performance measures I have particularly worked with, that is accuracy, precision, that is almost the ratio of the predictive as well as corrective kind of the samples, and with the total number of samples. Research gaps that is identified with the my research paper is particularly related with the acoustic features, feature extraction from the methods. There will be the long dependencies and short dependencies is also there, and there might be the risk of overfitting as well. So they require the large computational time as well. So these are some of the important areas which motivates to particularly bridge the research gap for this kind of the research work. This is the why this MSIF, that is the multilingual speech identification framework is good proposed. It is just because of it upgrades the performance as well as it gives the highest level side accuracy for the model. And this is a bias which basically having the workflow two directions, which basically give the attentive mechanism. That is, some of the points are basically assigned with some weightages, and that is to be attended, get more attention from the particularly the speech corpora to give with the results. These are the data sets that I have used. LDCIL that is a basic data set, and the Kaggle.com as well as the Mozilla Common data set. That these are the three data sets currently I am just working on. And lastly, coming on to the conclusion that the proposed network, that is a framework, multilingual speech identification framework, is a particularly promising approach which normally used to overcome all these kinds of the limitations with the existing model, with particularly the overcoming the dialect variations. That is basically the coordination between the number of samples of audio which are keeping one after another together. So which gives the come up with the very accurate results, and those results are lastly getting giving the accuracy above 90 up to 99%. So that is the summary of this model, why this is proposed model, and, which is promising in particularly this approach. Thank you.
Any question from the audience, please?
Thank you for the presentation. I have two questions. First one is, so you have used data for the Marathi language, Konkani. So they are all of, Devanagari origin, right? So if we add, suppose a Dravidian origin language with your four languages, then can we train the model with these five languages simultaneously? So will your model work or it will be different?
Of course, model will work because it is not specifically related with the language bias. It is basically with the variations in the language, dialect variations and sample variations that is to be processed with any kind of language. We can just take the multiple combination of languages, right from the Indian regions as well as the outer region that is not called any part of the world.
And the next question is, so you are giving input in the form of languages, right? Marathi, Konkani, and then what you generate is generating that you are actually discriminating as a real or fake by the discriminator. So I think it actually the application of GAN in this.
Yeah. Actually, my input is speech, that is the audio signal. That is getting converted into the spectrogram. That is the kind of element and have the magnitude, the points which is reflecting the magnitude of the images, and that is captured by the framework for process.
Probably his question is, what is the role of GAN here?
Yes. So the role of GAN is to discriminate the samples.
You see, GAN is primarily used to synthesize artificial samples, right? If you are using some kind of data augmentation to populate one of the small classes, that makes sense. But only for discrimination, you can do away with a very simple development as a 2-class, 3-class classifier. Why GAN? Is the question. GAN is majorly generating artificial speech samples. Is there something like that in your framework? Only that part needs to be discussed. If possible.
Actually, sir, I'm just started working on this. Might be.
So,
I'm not
you see, your framework is you have data, then it goes to GAN, then it goes to CNN, then it goes to ILS. All the, more or less, all the components are there. As far as I believe, the role of GAN in the classification end-to-end workflow is for generating artificial samples for a minority class. That is called data augmentation or data rebalancing. Yes. Probably something like that is happening here too. You can take a deeper look later. Okay. So thank you very much.
Thank the speaker and move on to the next.
Presentation, which has the title Spoken Language Identification using the Linear Frequency Residual Spectral Coefficients. And let me invite Dr. Hemant Patil once again for the presentation.
So I'll be presenting this paper on behalf of my student co-authors, by then the student co-authors, Krishna Parmar, Bhavi Singh Bora, and Shrey Machar. And also this work was done with as part of Samsung Prism program at DIIST. So there are some co-authors, Mr. Kiran and Mr. Balaji from Samsung Research Institute, Bangalore. So introduction to the problem. Spoken language identification, of course, already there is an excellent presentation by the colleague, is of course fundamental and primitive block for even the ASR to route basically the telephone call in emergency from the customer or the subjects, to a particular ASR in a particular language. So language identification can be used as a front end for this application. Of course, in the context of India, there are 22 official recognized languages as per the constitution, the 8th schedule. Many recent studies implements and uses the Bell frequency substitution coefficients and linear frequency substitution coefficient as spectral features for language identification. But however, these features are notoriously affected by the noisy environment and change speaking style. So further, in addition to the spectral features based on the vocal tag system, there are various prosodic features that are used for language identification, and they are known not to be at least relatively affected much as the spectral features. There have been work showing, like by Professor Lina Mary et al., the implementation of that, directly using linear prediction residual for spoken language identification. In this work, we extend this Professor Mary's work by mapping the residual to a substral domain in the subband. So that's the idea behind this work. And also we present the results for different orders of linear prediction. Well, linear prediction residual overview. In our one of the work in the recent past, about 5-6 years before, we proposed this feature set linear frequency residual substral coefficient for identification of spoofed speech, that is in the context of voice biometrics. That was done in Interspeech 2018, and this linear prediction residual that is represent the exception source information, which helps to identify the speakers. Here we exploit this feature set for the language identification. The LP residual contains the information of the excitation source, including the pitch, the fundamental frequency, rhythm, stress, and intonation, because they are all related to each other of the speech, and then there are fundamental components of speech, and it contributes to language components. So, Lina Mary and the other authors, B. Marites, have explored the research in this direction also. So, how to compute the linear prediction residual? So, you can see that this is like speech wave. Then we use articulation method, compute the top list matrix. Then we get the linear prediction coefficients. From this, we design the output filter, and then we develop, so inverse filtering to get basically LP residual. So residual means that the current sample minus the predicted version of it using the linear prediction. So the meaning of linear prediction itself is that it is not that only linear relationships are hidden in the sequence of samples of speech wave, There are also the non-linear relationships which are hidden in the sequence of sample of speech wave. However, to develop the computational efficient algorithm, the linear prediction-based approach, including the properties of Topli's matrix, is quite useful and it is very classic for last several decades in speech area. And linear prediction-based models, including its application in speech coding, speaker recognition, among speech enhancement, and many other problems, is very remarkable. So we first do the analysis of pitch strength. So distribution and preservation of pitch or the duration of speech can be defined as a pitch strength. So the languages spoken can be divided into three groups. Like one can be Mora time languages, such as Japanese, which is the Mora means the center is of course which is syllable, that is the vowel. The syllable time languages such as our Indian languages, the Hindi, Bengali, the stress time languages such as English and French. So this language structure mainly depends on the prosodic information derived from the excitation source of the speech. In our study to understand the prominence of LP residual, we calculate the pitch strength for syllable time language and stress time language. So we have done this analysis. So this graph shows actually the strength with respect to the F naught calculated using linear prediction residual, and of course you can see that there are two panels. One is for the you can say panel 1 and 2 is for pitch strength analysis for this syllable time language such as Hindi, and the panel 2 is for the stress time language such as English. Then the second row and the third row contain basically the pitch strength analysis using LP residual of different order. The second row is for order 12, third row is for order 16. So you can see here that there are some regions where, for example, this particular region where the pitch strength is indicated very prominently by the higher order like LP linear prediction order 16, which is missed basically here for the lower order of LP. And we will see in our results. We have done this analysis, this particular order 12 and 16, because we took the language identification performance, and this is the for LP 12 we got least performance, and this LP 16 we got best performance. So experimental setup in this work of language identification, we use the recently built standard corpora, very large corpora called Vox Lingua dataset. 107. The language classes used in our work is English, Hindi, Bengali, Tamil, and Punjabi. 80% of the data is used for the training. Then you will see that the 10% data is used for the validation and 10% is used for the testing. There are total 5,132 samples. We have used three feature sets. Two are baseline, MFCC, LFCC, and third one is a proportional. For all the feature set, we use 13-dimensional feature set as a static feature set, and the next 13 is a dynamic feature set as a delta system, and further 13-dimensional delta feature. So all the three feature sets are having 39-dimensional feature set for the uniformity and the pair definition. We use basically 40 subband filters for each of those filters. Then for each feature extraction, we use window length of 30 milliseconds and hop length of 15 milliseconds. So this already I explained. Now, once we get the LP residual, then we do basically something called framing, windowing, FFT, that is magnitude spectrum. Then we pass it through a linear filter bank, and then we take the log and DCD to get the LMR system. So what is the meaning of this? That earlier in the literature, people have used the processing of linear prediction in a full band. Now we represent this one in the various subband via this kind of filter band. The only difference here is that the filter band used is not with the male scale. We observe that with the linear frequency scale, we are getting the better results. And then we take the spectrum, we take basically its subband and then log and DCD. So this is like a step-step computation, but for the LP residual. That's why we call this feature as residual substitution coefficient, and the filter bank is linear, so it is called linear frequency residual substitution coefficient. In our work, we have used residual neural network, so we capture the complex information such as focal tag information and language specific information. Due to its skipped connections architecture, it allows to go deeper and capture both temporal acoustic feature as well as global language related features. We utilize 6 residual blocks
with increasing channels followed by fully connected layers and adaptive average pooling. This adaptive resonant network is similar to resonant 50. Now, for performing the language identification experiment, first we did effect of LP order on the language identification performance. So it is a language identification accuracy. This is the order. So you can see that we varied the order of LP residual. That means here. Here we calculate the LP residual here with different order of prediction. That we varied from 6 to as high as 25. So you can see that the least performance achieved for LP order 12 and relatively best performance achieved for LP order 16, which is why we have shown those pitch strength analysis for the least and the highest order. And we observe that the reasoning behind this is that this captures better pitch strength and captures the prosodic information. That information is very important for the language. As the performance comparison with the baseline, you can see that accuracy there is an equal error rate. So relatively, we are getting some marginal improvement for the proposed feature set. But what is important here is that we are using only the source feature here. Still, we are getting the better performance. So the next piece of work would be to fuse these evidences to get a better performance. So therefore, what we did a score level fusion of features with different fusion factor. This x-axis represents the fusion factor alpha, y-axis represents the accuracy, and this equation means that we take the one feature set plus we take the other scalar multiple another feature set. So one is fixed here, for example, if you see here the blue one, the blue tag line here. So this is like fusion of MFCC with LFRCC order 16. Why order 16? Because that is the one giving the little best performance. So we took that feature set. The red one is for LFCC with LFRCC. So yellow one is MFCC with LFCC. So you can see that the better performance is achieved, of course, for all the things and interestingly for equal weightage given to basically source and system features. That is, the MFCC and LFRCC gives an age, and then MFCC and LFCC is actually better performance. Same is also shown basically here in the form of the equal error. So which means that this is the yellow one is the highest one here. This is having the deep, relatively more deep here with the equal error, and also that is for the 0.5 weightage. We also have the feature level fusion. So we took the fusion of two feature sets like MFCC and LFRCC, then LFCC. So you can see that the fusion also gives better performance in terms of accuracy, both for the equal error rate. And this is done relatively for all the one. So of course, the system features are having a slight edge over the fusion with the other features. Maybe we can do the full evidences from this system features with LFRCC in the future. So to summarize, our study scrutinizes, investigates the significance, relevance, and efficiency of LFRC's feature set for the language identification task. As presented, language structure mainly depends on the prosodic information, enabling LFRCC to be useful for SLID tasks, as LP residual is the shared feature set, plays an important role in extracting the prosodic information from that process. One of the limitations of this current study is that it is presented only on 5 language classes, whereas in Voxlima there are 22 language classes out there. Our future research will be directed towards including more languages. So that's all. These are the selected references for our work. Thank you very much.
Thank you. Any questions from the audience, please? Anyone? Any question? So only one observation: when you are breaking this into sub-bands, you said, are they? Do you ensure their orthogonality? Signals within each sub-band somehow very less correlated. There should be something like
Yeah. So what we are doing for that is that there is a transform that we are using is a DCT here. So DCT, once the DCT output is here, so the DCT output actually makes the decorrelation of the features. Then also the features which are having the energy compaction in the features representation, and of course it is used for dimensionality reduction. So answer to your question is, I'm having, yeah, it's okay. Answer to your question is that the decorrelation of the features is ensured in this framework via DCT.
I see, yeah, because sometimes we used to use this quadrature mirror filter bands to ensure that their signals are in quadrature, that means very best correlated. But ECT, maybe, yeah, that might be one
So,
way.
so in this case, the key difference is, hello. Thank you very much for this question. Actually, historically, if you see the history, the quadrature mirror filter bands are invented from the Eastman and Gallant's paper on quadrature mirror filters for speech
Yeah.
subband encoding. However, somehow in the literature, if you see the filter bank that is used here, this filter bank, is not motivated from the quadrature filter.
Yeah.
The filter bank is actually rather, so the difference is the one that was invented by Eastman and Gallant around 1976 or so. That was actually from the impulse response in the time domain. There is a closed form expression of impulse response of each subband filter.
Right.
Okay. So I can give an example. Suppose the HN is, let us say, impulse response of the low pass filter. Then the impulse response of the high pass filter will be -1 raised to 1 minus n g h of n 1 minus n.
Right.
This is the quadrature mirror filter bank condition. So, which means that we have an exact mathematical representation for the impulse response. And hence, if you take their Fourier transform, that is the frequency response, they will be crossing each other at pi by 4, which is why this is a quadrature mirror filter. Now, in the speech literature, wherever the MFCC is used, LFCC is used, and now these feature set, and many other such approaches, somehow these filter banks are actually simulated as a triangular filter shape, and they have no mathematical representation in the
closed form is almost impossible.
Yeah, for that these filter banks. So
Yes.
this is the discrepancy in the literature. What is done then? That firstly you pass the so why this is a discrepancy? The idea is that this simulated filter bank, which was like a original paper by Davis and Mergelstein in 1989, they are simulated to give the Bell frequency system MEL, which is from the Weber's law of human psychology. It gives basically linear frequency resolution before 1 kilohertz and the logarithmic frequency after 1 kilohertz. So the attempt here is to mimic the Weber's law more predominantly than the quadrature mirror filter bank, right? That is one thing. So what is done then after subband? There is also subband energy computation, and then those energies, let us say 40 filters are used, so you get 40 subband energies L2 norm. Those 40 numbers are given to DCT for decorrelation.
That way is coming. Yeah. Thank you for clarifying this. So, if there is no more question, let us thank the presenter. And that marks probably the last paper. This is the last paper for this session. Thank you all for attending it. Have a good day.
On.
Thank you, sir, for conducting the session. Now we request Dr. Tornoy Boshu of ISAR Bhopal to please come on stage and felicitate Professor Das with the moment. Now we have a break. We meet here again at 12:30 p.m. for the first keynote talk of the day, and refreshments will be arranged outside the auditorium. Thank you.
Don't touch.
Hello. Hello. Check. Hello. Check.
check.
একবার দীপকতা বলবে তো
বলবো বলো ঠিক আছে আরো বল এত বলে যাবে
এই আরেকজন দাদা গেছে তুমি একটু বলো তো দাদা হ্যাঁ টেস্টিং তুমি পারো
ইউটিউব লাইভ স্ট্রিমিং হচ্ছে হ্যালো এখন এক ঘন্টা পর
অফ করে দাও
কোন সাড়ে 12টা থেকে
ওটা মজা হয় মানে ইন্টারেস্টিং উনি দারুণ বলেছেন সোজা করে বলতে
उषा आंटी मला भी मैसेज करते हैं उषा आंटी मला भी मैसेज करते हैं
আসছে এটাই আসছে এসে গেছে হ্যাঁ পাওয়ার কেবল তাহলে নেটওয়ার্ক কেবল কোনটা নিচেটা না উপরটা চলে আসছে দুটোই चष्मा दिसतो ना काही असं वस्तू कंटिन्यू काही वाटत नाही चष्मा घालून प्रेझेंटेशन केलं चष्मा होता दिसत नव्हता ना मला काय बोलतो वाटतं त्याला काही डिस्टर्ब होत आता तो आधी जे तुझी करायचं आलं बाहेर नुसतं पोराचं शांती मला म्हणून तुम्ही तरी कमिटी मध्ये आहे तुम्ही काही काम नाही करणार म्हणतो मला फक्त एक मानधन म्हणून ठेवा जेवढं महिन्यात एकदा येईल मी तिथं सांगू आणि निघून गेला मग तू चालू कमिटी मध्ये माझ्यामध्ये तू अटेंड करायचं मी तुमच्या बोललो की मी काही काम नाही करणार तुम्ही फक्त मला सपोर्ट म्हणून घ्यायचं असेल तर कारण माझ्या पोरं 10वी मध्ये जाणार मला टाइम नाही निघून जाणार मला तुझ्या मागची सोसायटी का ते आणि आलायच आहे ना आपल्या कमी कुठला थोडी घ्या ठीक आहे मी असं 3 वर्षाला फोन केला होता काय करतं काय चष्म्यावर काय दिसतो काही दिसत नाही तर मी कुठे सरळ दिसतं ना